Morning. How are you?
How are you?
Good. So today we are finally moving to interesting stuff, magic stuff. We are starting to talk about robust control. And this is happiest part for most students because you don't really need to know anything on that course. It's not really even part of that course. And you don't have any homeworks on that. So you actually can learn now something instead of just learning for homeworks. All right, do you have any questions on the previous lectures? Homeworks, projects, other things? Issues? Have you started doing your project? Because probably like in a week or so, you will need to start reporting on it. So you don't have that much time. And I will ask you also to send me email about who your partner is for the project, if you have any. Okay, if you plan to have a partner and do project in pairs, it's okay. So you will let me know because I need to plan how many presentations we need to do at the last week of the semester for that project. Okay, so I will need to know how many projects we will be reporting on. Okay, so first of all, we'll start with motivation for robust control systems in general. And robust control came after modern control, started approximately in 80s, 90s, most of the time. But research in that domain still continues to this day. So robust control is more modern than the modern control. Okay, now we have more of the nonlinear robust control and other things of modeling which came up in 2000s, but this is started at 80s. And it started with a few basic ideas which I think are very useful for other domains as well, not only specifically for controls and robust controls, but it's more about how you think about different ideas and how you come up with things which seem to be impossible, but then you just solve the problem which seem to be impossible to solve. And this is why you need to be aware that such methods exist, where you have things which look like magic in a way. And the reason that people started to develop all of these theories after modern control is because typically when you develop your system, you estimate the practical plant from particular measurements, right? And in these measurements, you have a lot of challenges with estimating the parameters of the system. So if you have the state space control matrices, you don't know them exactly, okay? So I'm giving that as exercise, giving you particular numbers in the matrix A and matrix B and matrix C. But technically, how would you know these numbers in the first place? So you have some motor or you have some bigger thing that you want to control. How would you know what are the matrices A, B, C, D? So you need to estimate them somehow. So you measure all kinds of things in the system, but your measurements are not great typically. And you get all kinds of numerical approximations. You have all kinds of challenges with your sensors and measurements and so on. And every time it might be a little bit different also if you're repeating the same type of measures. So how would you deal with that uncertainty in the model? You can deal with that as just modeling as noise, as we did with Kalman filter, right? You can say, well, everything I don't know about my system is some sort of noise, and I will assume something on the distribution of that noise, which is also possible. It's okay way to do that. But uncertainties might be more complex than that, than just Gaussian distribution of some kind, right? So it could be multimodal, it could be particular ranges of variables that could change in particular ranges, and so on. So it's a little bit more complex than just assuming that this is some sort of noise, okay, with zero mean. It could be not noise and not zero mean. All right. So this was the initial motivation to develop new types of definitions of what uncertainty is and how you can deal with it later, how you can control the system given these uncertainties. Because the motivations questions was that for that would be how you stabilize and develop system with particular performance, because this is what typically we want from control systems. if the parameters are uncertain, so you don't really know the parameters exactly. You know something about them, you measured something, but they kind of having some tolerance, okay? They can change, maybe, in time, and you don't know exactly how, which is typical things that we see in all physical systems, right? It's natural for us to assume that we'll have that type of troubles. Another kind of problems that we want to deal with, let's say your system has differences in frequency response. So what we know about frequency response, typically we deal with body diagrams in frequency response, where you have Fourier transforms and all these body diagrams which are showing you how system responds to particular frequency, right? So if you put input of particular sinusoidal input, you get different phase and different amplitude of the output. And depends on the body diagrams, you'll have different phases and different magnitudes of that output signal, sinusoidal inputs. Remember how you develop body diagrams in general, how you even estimate systems, so you can do very simple, theoretically simple computations. You have some sort of system that you want to estimate, you give it some sort of sinusoidal input, and if it is LTI system, linear time invariant system, you get another sinusoidal signal, okay? All LTI systems for sinusoidal input will give you sinusoidal output. It could be different phase and different amplitude from the input. So if you're putting input with amplitude, let's say 1, this is your input sine wave amplitude 1, particular frequency, you can measure. For that particular frequency, you can measure what is the shift of phase happened to the output and what is the change in magnitude happened to that output. So you divide in that magnitude by 1, and you get, for that particular frequency, you get point on the absolute value of the transfer function or system, okay? Which means the ratio between amplitude here and amplitude here, this is your body gain. It's gain of the system. What was the gain? How much you amplified the output. But since you're doing that in log, so typically you're doing that in dB, in body diagram, right? You're doing log on that, which means that the division will become, practically speaking, subtraction in log, right? This is why body diagrams, you can add plots of body diagrams of two systems. Like if you put in two systems in series, you can add diagrams, body diagrams, like point by point, because this is log. Okay, multiplication and division in logarithms is addition or subtraction, right? So you get at one point, then you choosing frequency, different frequency, you get another point, then another point, and whatever. Okay, to get the body diagram based on the ratios between amplitudes for different frequencies. Same thing you're doing with phase. You're measuring difference of phase of that signal compared to that signal. This might be like 0 phase, starting at origin, sine wave, right? And this will be maybe like that. So you'll be able to measure the difference of phase here. This will be that point here, whatever that phase is. And so on, and you can measure multiple phases, and this way you can identify body diagram from practical system. So you're just sending all kind of sine waves to that system and measuring some sine waves as the output, measuring phases and gains. Now, this would definitely work only for stable systems. If system is unstable, you put in sine wave, it's infinity, not that interesting. So you cannot do that for unstable systems. But for stable systems, this is what you can do, technically. Especially if they are close to be linear. But the problem is that most systems are not linear, or practically all systems are non-linear, okay? So in reality, you cannot really do that. And the reason is that body diagram for nonlinear systems will depend on your inputs. So it will not have single body diagram. It will have a bunch of body diagrams for different things. You'll get different body diagrams, okay, for different inputs. So it, like transfer function will depend on the input, technically speaking. So you'll not have even the definition for transfer function. and you will not have body diagram as is, as you know, for LTI systems, if the system is non-linear. So there is no even meaning to talk about real body diagram or transfer function for non-linear systems, because it is defined only for linear systems. So our thing is that what we want to do is to define, instead of one body diagram, family of possible body diagrams for all kind of inputs and all kind of potential changes in the system. So you have envelope of body diagrams, for example, right? So you have expansions of the same theories of linear control to uncertainties in frequency domain. So in frequency domain, you'll have, instead of single body diagram, you'll have like range of body diagrams. So frequency response might be in that particular range. Another interesting question that we can ask in robust control is how to find the entire family of all possible stabilizing controllers. I mentioned that question before because this seems to be completely impossible. But after you learned a little bit about modern control, it starts to be a little bit more kind of feasible, because you are saying, well, technically, if I want to stabilize my system, for example, right, all I need to do is to choose location, all possible locations of all possible poles in the left semiplane for continuous time system, right? And then I will just design all possible controllers by choosing, like sweeping the entire left semiplane with all of the possible combinations of all of the poles, right? And the system will be stable, no matter where I choose them. It doesn't matter, right? And we have already formula to compute K for that. But you have expansions and extensions for the same principle, where you can choose your location of poles and then get any stabilizing controller you want, okay? But this extension will be for actual serial controller, not even state space controller. So you'll design controller and observer, and you want to find particular realization which will be serial controller, not even in the feedback as regular K goes, but regular system like that. So you'll have system of regular kind like that. Okay, that kind of controller for your plant, like serial transfer function control. So you want to find now all possible transfer functions which could be here and would stabilize your given plant, which is given in state space. Which sounds a little bit more complex problem, right, to solve. It's not exactly that easy as like designing all of the possible K's to stabilize that thing, right? Because it's a serial control. And in post course on control systems, typically you would struggle a lot to find even one controller of that kind, right? You would kind of play with parameters until it converges, until it's like, and then you modify the parameters and playing with the parameters through locus design, phase margin, gain margin, all these tools that you learned in the initial course on controls. And you struggled to find even one. Now I'm telling you, oh, I can give you actually formula to find all of them, all of the stabilizing controllers possible. You pick any random transfer function or any random controller, like design, and it will work out of that family. And the algorithm is not that complicated even, okay? It's not like I need to do optimization. I can do that by hand. Okay, I can find you the entire family of all possible controllers, which again, sounds like impossible. It's weird that it's even possible. And all the theories, I'm just sampling a few pieces from robust control. Obviously, we will not learn anything in robust control in depth. I will not prove anything in depth. I will just show those pieces of magic which are coming from different areas, which seem to be impossible, but people found solutions for these problems. Okay, and we will start with robust magic. How to stabilize polynomials first. So we have very simple problem, very easy to formulate. So you know that if the denominator polynomial of the system is stable, then the system is stable, is how it is defined, okay? Which means all of the roots of that polynomial should be in the left semiplane. That's how we know that for continuous time systems. Now, that would be easy for all the degrees less than 5, because we can compute by hand roots of the polynomial of order less than 5. You have formula for that. You have like quadratic polynomial, cubic polynomial, you have formulas until degree 5. From degree 5, as I mentioned some time ago, you cannot even find formula. It's impossible to find formula which solves generic polynomial of order 5 and higher, which means there is no formula and will never be, unfortunately, for us, okay? Which means you cannot write it by hand, but there are still numerical solutions, and since we are always using approximate solutions for everything as engineers, we don't really care. We will give it to MATLAB. You have polynomial of 100th order, give it to MATLAB, it will find 100 roots for you, okay, numerically. Approximation, of course, not exact. You'll have maybe some issues with particular polynomials where the roots will not be exact or close enough to reality, okay? But in most cases, it will be fine. You'll be able just numerically to converge to all of this 100 roots of your polynomial. So for us, it's not a big issue to find roots of a polynomial. For mathematicians, it is, but for us as engineers, we are fine with approximations, all right? But now I'm asking exactly the same question, finding roots of the polynomial and where they are. But polynomial, I'm not sure exactly about the coefficients of that polynomial. And those coefficients could change in particular range, any of the coefficients. And here's how I will define it. This is interval polynomial. So interval polynomial is defined like that. You have polynomial of order n. So you have s to the power of n plus interval of 2 coefficients. So these are 2 numbers, a bottom bar and a upper bar. Okay, so bottom bar is the minimum that number could take, and upper bar means maximum that number could take. So it's range of numbers. It's just interval. And you can write that like 1 through 3. So any number between 1 and 3. Okay, this is what it means. That type of writing, okay, so far. And each coefficient will have its own range, whatever it is. And here's one example. So that second coefficient will change from 1 to 3. So it can take values 1, 1.1, 1.67, whatever. Any value between 1 and 3. This coefficient will take values between 5 and 50. This coefficient will take values between 7 and 12. Okay. Obviously, the first number should be less or equal to the second number in the interval. So it's like from smaller number to bigger number. Okay, but they could be the same, which means you have actual constants. So it could be from 5 to 5, which means it's just number 5. Okay, so far, so these intervals could be actually constants, a single number in the interval. But this is an example of that type of thing. And if I can pick particular realization of that polynomial, I will get something like that. Obviously, you have infinite number of possibilities here. Any combinations of any of the coefficients could be fine in the ranges that I predefined. So this is just one of them. So for that particular one, clearly I can find location of the roots. But how can I find location of the roots for that entire family and to say if they are stable or not? The question is very simple. Is that entire family of polynomials is stable? Which means all of any realizations of these polynomials having roots in the left semiplane. So this sounds as a horrible problem to solve, because how would you even start thinking about that? So initial thing that engineers are thinking about is grid search of some kind, which means let me like run multiple for loops for each coefficient on really, really tiny grid, which means tiny step. And let me check all of them in those like multiple for loops and see where the coefficients are, right? So you're finding those millions of different possibilities. You're running all of the coefficients one by one, checking all of the possibilities, direct approach. And then if everything is stable, then you're saying, well, it seems to be stable. But is it really true for everything? Like, would you trust that that grid covered everything you wanted to cover? And here's one simple example of root locus. And you know that on root locus, you have that kind of magenta Tiny square here is where your particular realization of your system is. So clearly this realization is unstable. But if you are looking on that root locus, almost entire root locus on the left semiplane, which means almost for all possible parameters that you would choose ever for that particular thing, particular system, it always will be stable, except this location, where they moved from here somehow, crossed the boundary for a little bit, and then ran back again, which means that it's almost always stable for almost all points. But what do you do when you're doing grid search? When you're running all these parameters? Practically, you are discretizing that curve into particular points and you're checking at these points. So what if you missed that particular point in your grid? Like, would you put that controller on your point engine? Like, it's almost always stable, almost, but sometimes not really. Who knows? If it overheats over a particular point, then you get that parameter moving a little bit into the area you don't want it to be, you crash it. All right, not a great idea, I guess. So you need actual analytical tool which helps you to check if your system is always stable, entire family stable for all possible parameters in given ranges of tolerance. Okay, this is the overall idea that people came up with. So we will continue that idea of root locus here, and root locus is just one possible idea that you can use here, but here's the idea. So what do we know about root locus? We know that if particular parameter in our system is changing continuously, this means that the roots are also moving continuously. And doesn't matter what parameter, which means you can have like 1 million parameters in your system, but if you change that parameter like tiny little bit, the roots also will change tiny little bit. Okay, so they will not jump from here to there, unless you have degree drop in your polynomial. Okay, so if you change in the number of roots, then they can jump from place to place. But if this is same order polynomial and you move some parameters of that polynomial, roots are also changing continuously from the previous position. And this is why we are typically using that type of polynomials where you do not have any degree drop here. So this is multiplied by 1, as you see. So this coefficient is 1, monomial polynomial. Okay, so we do not have any degree drop here. So this is like overall idea, which is very important for that entire robust control theory, that when you change in parameters a little bit, the roots are changing a little bit continuously. Okay. This also means that if you have one particular realization which is stable in that family, so picking any polynomial in the family, and you see it is stable. To make that family unstable for particular polynomials, it needs to cross j omega axis somehow for a particular set of parameters. Because all of these roots from that initial position for a particular set of parameters, it was all stable, right? You're starting with stable polynomial. Then you need to have some particular trajectories of these roots moving around continuously as you change your parameters continuously within your family, right? To make it unstable, they somehow need to cross j omega. They cannot jump to the right side. Okay? They need to cross through, which means that your polynomial must have for a particular set of parameters zeros on j omega. Okay, so there is some set of parameters, including omega, for which this polynomial will be 0 on the j omega axis. Is it clear what I'm saying? So you have trajectories of roots. These trajectories to become unstable from stable to become unstable, they somehow need to cross the j omega, which means you need to have some points on j omega where you have solution to that polynomial, which is 0 of that polynomial. Okay. So this is overall idea, like where we start thinking about solutions for that type of problems, where you convert in one problem into another problem. Can you find roots on the j omega axis of the polynomial? No. It's simpler than finding roots for just generic polynomial. Now you the roots only on the j omega axis instead of general S, which is complex plane, right? So this is called zero exclusion principle, okay, which is the cornerstone of all the theories for polynomial robustness in general. So given particular polynomial with interval coefficients, now you know that each parameter is changing continuously within these intervals, because intervals are like for each coefficient you have unique single interval. It's not jumping from one interval to another interval, right? So it's continuous interval. It's not like multiple intervals for each coefficient, which means that if you change parameter a n minus 1, it will change continuously in that interval somehow. Okay, it could go up and down, but between these two numbers. So it's continuously can move on that interval. And each parameter is moving continuously on that single interval. It's not jumping anywhere. So you do not have any discontinuities in the parameters for that particular family. And you can expand that family to other things, but I'm talking about this in the most simple case here. Okay, so continuous change in parameters will give you continuous trajectories in roots of that polynomial. We start with stable family member, which means we just pick particular number in each one of these intervals, and we see that polynomial is stable. And then if you start with that stable polynomial, you need to cross j omega axis to become unstable, and then the entire family will be unstable. Unstable family means not that all of the polynomials in the family are unstable, but that you have at least one which is unstable. So it's unstable family. It's not that you have one unstable polynomial in that. So theorem states that if you have at least one stable polynomial in the family, and the entire family is stable if and only if no polynomial has 0 on j omega axis. This is what we claimed so far. This is zero exclusion principle. Now let's try to unpack it a little bit. Right? Any questions so far? Okay. So what does it mean crossing j omega axis? Crossing j omega axis means that if I replace S with j omega, for that particular omega, this polynomial will be 0. Right? I just replaced S everywhere with j omega. So for given omega, where it is 0 of that thing, I will get 0 of that polynomial. Okay? So I do not want that to happen for any omega. This is the idea. So I want for all omegas this not to be true. And for one polynomial in the family to be stable. And then the entire family is stable. Right? Also, I want to say that it's enough to look at omegas which are positive omegas. Obviously, omegas can change from minus infinity to plus infinity, right? It's like entire frequency range. And typically in body diagrams, we're using only positive one. Why is that? Why don't we care about negative ones? Negative frequencies. I'm saying that I care only to check crossing on the positive axis, and not on the negative axis. Why should I care only positive?
Is it symmetric?
It is symmetric. So we know for any systems that you have, that you have always conjugate roots, right? So if negative root kind of on the bottom part crossing the j omega axis, you know that another positive one crossing j omega axis at the same time. Okay, they're all symmetrical, okay, with regard to the x-axis, with regard to the horizontal axis. Okay, they all move like that. So you have pairs of poles, they are conjugate poles. You always have that. Remember that? Yeah. That type of poles where they are moving on particular trajectories, but they always coming in pairs for complex poles. Like real poles are not, doesn't matter. But for complex poles, they always coming in conjugate pairs. So if negative crosses, positive crosses at the same time. So we can check only omega, which is positive omega. And we will deal only with positive omegas. Now we want to define something which is called value set. So value set is all of the possible values for the polynomial p for a given particular omega. So you're fixing the omega. It will be particular positive value or zero, positive or zero, okay? And then given all these parameters that could change in various ways in intervals, right? You will be able to compute values of that polynomial for that given omega and set of parameters. Let's say you pick particular set of parameters, say 1, 2, 3, 4, 5, and omega. All right? So all of them are numbers. Clearly, since this is j omega to the powers of whatever, you will get some complex number here, plus some complex number here, plus some complex number here, plus some real number here. Okay? So that sum will be some sort of complex number. Right? Clear so far? So for each given value of a's and omegas, I can find particular complex number which corresponds to the value of p of omega. So p of omega is just set of complex numbers for a given set of a's and omegas for a given omega. Okay. Now, how it will look like in space, in complex space. So for given omega, which I will denote by particular red point, okay, I will have something like that. It could be all kind of, depends on the family that I define here, okay? Now, the point is that this will be connected set, which means it's like single blob. Why is that? Because again, when I'm changing continuously parameters using particular connected set within connected set, the roots also will be, the results of P also will be connected. Okay, this is theorem in complex functions. All right, so when these values are continuously changed for a given omega, the sum of the values also continuously change. Okay, I'm not proving it, I'm just claiming it. Okay, so you will get some sort of particular value set. This is this area inside of that blob called value set, which means all of the possible values of P for given omega, right? They will be inside. For different omega, you'll get some other value set. Okay, this is for second omega, third omega, fourth omega. You'll get that thing kind of moving in space as a function of omega and changing the shape somehow. Okay, but the point is that it is connected set, which means it's not multiple blobs, it's single blob, okay, of some particular shape. This is the overall idea of that value set for this continuously changing parameters. All right, any questions? Okay, so let's try to do that experiment with grid search on a particular sixth order polynomial like that. So you have particular polynomial of that kind, and each value is changing particular parameters, and here is my MATLAB code, or you can use any other code to plot it. Omega is changing in particular range with particular step, parameter A0 changing in that given range with that given step. You can make steps smaller and smaller, you'll have more and more density, right? You'll have more computations, obviously, but more density to these plots. And then what I'm plotting is actual evaluation of the value of the polynomial for this set of parameters, for all of them. And each one of them will be a single dot. Okay, so for the initial omega, which is 0, you will have probably points somewhere here. So that set of points. Then for omega equals 0.1, you'll get that set of points, then that set of points, and so on. For all these steps, you'll have multiple things kind of moving around like that. And I can control the density again with this time step, coefficient steps. Okay. Obviously, these holes need to be closed. Okay. All of these holes that you have here are because I'm doing that step. Okay, and missing some of the values in the middle. They need to be connected set. So this is connected set, like all this, like 3 columns should be all connected between them. and all the points need to be filled between them. They need to look more or less like that. This is the ideal look. Okay, but all of them should look the same way. So the holes that you see in these rectangles are because of the step size that I have chosen. Okay, you can make it more and more dense if you want to. So look what happens here. The point is that to make the system stable, you need to have one stable polynomial in that family. And this value set should not include origin, which means they never should be zero. This is what it means, right? If they include origin point, which is that point, 0, 0 point, 0, 0 point here, then they become unstable, which means they are actually crossing j omega axis. So this thing has 0 on j omega axis. That's what it means. If that thing includes that point. Is it clear where I'm going with that? So all I need to test for that polynomial if any of these rectangles actually touching that point or including that point. If yes, then this is unstable family. If it is not, then it's stable family if you have at least one member which is stable. This is all you need to know. This is coming to very important, interesting theorem now. Because now I need to check only what happens to these value sets instead of checking the original polynomial. And now you can notice that the results look very specific. They all look like rectangles, right? All of the value sets for pretty generic polynomial, I would say, k of 6 order. And I'm not proving it, but you can actually prove that for any polynomial of any kind with this interval coefficients, you will always have these value sets as rectangles. Now, you have that brilliant idea. If they are rectangles, I don't really need to build all of these points inside of the rectangles. Why? Because all I need to know is this rectangle includes the origin for any omega, right? If you have such an omega for which this rectangle will include inside that thing. But what do you need to know for that? All you need to know is where your corners are of the rectangle. This will give you enough information for where the origin is compared to the corners, right? So if your corners are kind of outside of the origin in the same quadrant or in quadrants on the same side, then origin is not included. But if they are in the diagonally opposite rectangles, then it is included, right? So all you need to know is practically where your two corners or maximum, minimum of the sides, which means 4 numbers, technically speaking, which are defining two corners or defining maxima and minima of the box. This is all you need to know. And the magic thing, which was developed by Vladimir Kharitonov, is that you actually can find these polynomials which will give you these values of the extreme boundaries of that rectangle. And they are kind of easy. And we almost got to them in the previous calculation where we divided the j omega, inserted j omega, and we will see how we get there. So we will develop a little bit the same polynomials we talked about before. So it has a polynomial p, which is j omega to the power of n plus the first coefficient, blah, blah. And we want to know when that thing equals to 0, or actually not equal to 0. That's what we want. Okay, for a particular omega. We will rewrite that a little bit. Okay. We will take imaginary and real parts separately of that polynomial. Okay, because if you're looking on that rectangle, all you need to know what is the minimum of real of values in that value set, what is the maximum of reals in that value set, maximum or minimum of the imaginary part, and maximum of the imaginary part, okay, of that value set. This is what you need. So let's divide that into real and imaginary part. So here's how it will look like. I'm just writing specifically, more conveniently to write the other way around, from right to left. Okay, so you'll get A0 plus J A1 omega plus J squared, which will be -1. Okay, this one will be minus J. This will be J to the fourth will be -1, and so on. Right? Remember powers of J? So what is the real part here of the polynomial? So it's A0 minus A2 omega squared plus plus minus signs are changing, okay? And then you get powers of omega, which are even powers of omega, okay? So you get something like that, all right? For imaginary part, you can take J out, and then you get A1 omega minus A cubed omega cubed, like all of the odd powers of omega. But pay attention that omega is positive. So all of these numbers are actually positive. Okay, so omega squared is obviously positive, and of course, all of them are positive. Okay, so the only thing which can change sign is actual coefficients, right? So we are looking again for maxima, minima on the real part and the imaginary part, and I'm just copying this real and imaginary parts from the previous slide. So how do you think we can find minima of that thing? And you know that A0 has minima and maxima because this interval, right? A0 is in particular interval from minimum number, could be positive, negative, it doesn't matter, but you have minimum of A0, which is A0 bottom bar, okay? And you have A0 upper bar, which is maximum in that interval, okay? So how would you find, for example, minimum of that expression? Like what kind of values would you choose? For A0, A2, A4 to get minimum possible out of that entire expression for all the possible values. What would you choose?
One.
What one?
Just one.
What do you mean by one?
If I replace all A0, A2, A4, everything by one.
No, you don't know what they are. You have just intervals for them. You have A0 bottom bar, you have A0 upper bar, and everything in between. So you can have value A0 could be between A0 bottom bar to A0 upper bar. So you have that thing. So A belongs to that interval. And you can choose any values out of that interval. But I'm asking, now you want minimal value to that sum. What would be the values that you would choose to get minimum possible to that entire real expression?
So negative value?
It could be positive or negative. It could be anything. I mean, any of these values could be positive or negative.
Yes.
But you know that you have minimum value, like you can have it like -1 to 5, whatever. So you want minimum out of that interval, what would you choose?
Would it depend on the sign in the terms? Would it depend on the sign in the terms?
Not at all. So this could be +1 to 5 or -1 to 5 or -1 to -0.5. Could be all kind of signs. Doesn't matter.
Right, but here,
But you want minimum. It doesn't matter what signs are. Yes.
like here, if you wanted minimum, wouldn't you want to choose like the maximum value for A2, but then the smallest value for A4?
Exactly. That's what you choose. So for A0, you choose this one. For A2, you choose this one. And so on. Because like first comes with plus sign, and you know that this is positive, right? It could be even negative number, it could be -1, but this is like the smallest out of possible ones. Okay, so you're choosing -1 in that case for A0, and then you're choosing maximal A2 because you're subtracting it. Okay, so you want to subtract as much as you can to get your minimum, right? And same thing, you're choosing minimum here, and then maximum for the next one. So you get like bottom bar, upper bar, bottom bar, upper bar, interchanging, okay, to get minimum. What do you do to get maxima? The opposite. So you're choosing maxima, minima, and so on, okay, for all of them. Now, very similar thing happens here, right? Since omega is positive, and we assume that omega is at least not negative, for minima, you're just choosing minima, maxima, maxima. And the other way around for the maximum of imaginary part, okay? This way you find these boundaries. Given these boundaries, you can identify everything you need to know. So again, I'm not proving here anything, it's more hand waving just to give you some intuition of where things are coming from. But here is the Kharitonov theorem, which is that cornerstone theorem for polynomial robustness. Okay, this is just first step in that entire theory, which states that if you have that kind of polynomial with interval coefficients, all you need to do is to check 4 separate polynomials. If all of them are stable, then your entire family is stable. All right. And as you can see, like, look how it looks like: minima, maxima, and so on. And same thing here: minima, maxima, and all of the other combinations that we saw before, all of the 4 combinations of minima and maxima. So if you check these 4 polynomials, and they are polynomials with constant coefficients, right? They are with given numbers. It's not anything in between. You just need to check 4 polynomials with constant coefficients. If 4 of them are stable, your entire family is stable. This is the magic of that theorem, which was completely unexpected that it's even possible to validate. And here you just check 4 polynomials with constant coefficients, you get entire family stable. Isn't that magic? Any questions? And now we move to a different idea, all stabilizing controllers, which is also called Euler-Kuchera parametrization. Very interesting theory. And we touched a little bit that theory when I asked you all kind of tricky questions. If you remember at the beginning of the course, we went through all kind of design of controllers in a silly ways, where we talked about, like, can I just use 1 divided by g as my controller, and then 1 divided by g times g will give you just transfer function of 1, and it's perfect controller, right? You get full tracking, exactly what you want. But unfortunately, it's not that easy. So here we will see the actual way to do it right now. Okay, now we want to do that in a correct way. And I hinted on that correct way at the beginning of that course, but we haven't went to the actual solution. So now I want to show how you find all of the possible controllers for your system. Okay, so we will assume that you have regular controls 1 type of system with transfer functions, and the transfer functions are given in a regular simple way. You have some controller, you have some plant, and you have regular loop. You can ignore the noises and disturbances. In that case, this is Y, this is reference, control effort. Okay. So you have regular system, you want to design all of the possible controllers which are stabilizing the generic plant, whatever the plant is, given by any transfer function you want. All right. So here we assume that f equals to 0, and S will be, it is set, okay, the definition. It's all stable and proper rational transfer functions. Now, transfer functions are not always rational. Sometimes you have all kind of delays in it. So you have like exponent to the S tau or whatever. We are using just regular rational transfer functions, okay? Whatever you saw in the course before. Also, what is proper? You remember what proper is? You have proper and strictly proper. Strictly proper is subset of proper. So what is proper system? Remember proper systems. So proper means that you have less or equal zeros than poles. It also means that the system is practically speaking causal system. Okay, so it's not dependent on future values, like derivative, for example. So derivative is not causal system, but integral is. So proper systems means that they are regular physical systems, practically speaking, okay, that develop in time. So you give particular inputs, you get particular outputs. It's not like you're using future outputs to compute how system behaves, right? It's causal system. So here is the algorithm. So if you remember, we have closed loop transfer function here. Will be CP divided by 1 plus CP. This is a closed loop transfer function for that controller at that plant, okay? And we want that thing to be stable, right? So my proposal, initial proposal is very simple technically, which I mentioned previous time. Why not to compute C algebraically on that equation? What would you get? You just multiply that thing by that. So you'll have T plus TCP equals CP, right? Now you need to compute C. So you put CP minus TP equals T, right? Actually using here, maybe I should use something else, but doesn't matter. And then you can compute that C equals T divided by P minus TP. And there is problem with that. Okay, what is the problem?
I have a question.
Mhm.
Why don't we take the CP into 1 minus T?
I'm sorry.
The common value could be also the CP, right?
This one?
No, TCP,
TCP is this one?
yes, minus CP. So I can also take the indirectly CP.
Can you show me? Is there any mistake here?
No mistake. I'm
Mhm.
just my question just. I mean this one, okay?
Mhm.
I can also take the
Yeah, I'll do the parentheses. Yes, sure. You can also write that as this one divided by P. This will be 1 minus T. Yeah. You do it in multiple different ways. But the point is, this is okay, kind of, but why nobody is doing that? Like you had entire Controls 1 course to design controllers for your system. Why nobody told you like, oh, pick any random desired stable transfer function, right? And then compute that. Done. The closed loop transfer function will be that, right? What's wrong with that? You see, like, you remember, like, so much pain to design these controllers for Controls 1. Here, Controls 1 course, 5 lines of derivation. Here's your controller. Pick any T you want. Stable, with parameters that you want, with characteristics that you want in closed loop, whatever. Isn't that perfect? Like, why people are not doing that? This sounds like pretty solid, right? This is a very tricky question. Do you know why it is tricky? Because nothing is wrong with it. It's completely fine. Okay. You always will get that. I mean, your controllers will always be like that. All of your controllers will be like that. But the issue here is that sometimes when the plant is unstable, you will have, if you choose controller that way directly, you will have cancellation between unstable zero and pole algebraically. And this is a problem. You remember why this is a problem? When you're canceling unstable zero or pole? It is a problem, okay? So that kind of design is fine for stable systems. And yeah, you'll get some cancellation of stable zero and pole, not a big deal. So you'll not be able to control maybe convergence to some extent, potentially, okay? The thing is that when you are choosing your T of closed loop, you never know if it will happen or not. Like you cannot like just visually see it and predict that this will happen until you actually compute it, right? So how would you choose a T of closed loop, desired T closed loop in such a way that this will not happen? This is a problem. So it's like, yeah, you can do that, but you might get in trouble if you're not actually validating what have you chosen for your closed loop. Okay, and this is why this is not, how to formulate that, not great technique to design controllers in closed loop, because you don't know what you will get based on your choice of T closed loop. Sometimes you get something good, sometimes you get something bad. Okay, and you cannot know that from the beginning when you choose it. So you do not know how to choose it in correct way. Okay, so this technically gives you some ways to choose it in a way. Okay, so it divides that plant into stable and unstable first. So if plant is stable, this is very easy. Choose any possible transfer function which is in that set. And to remind you, this set is stable and proper. So pick any stable proper transfer function, whatever you want, and call it Q. Okay. Take your plant P, compute that equation, this will be your controller. And obviously, there is no other controller because it's just algebraic equation, right? You cannot have any other controller. So it's if and only if. So for all possible Q in that set, you will get stabilizing controller if P is stable in open loop. So if P is stable in open loop, just use that. Okay, this is that easy. Okay, and pick any transfer function you want. But if it is unstable, then you have a problem. Not exactly a problem, but you need to work harder, let's say. All right. So here's what you need to do. This is entire algorithm, how you find all possible stabilizing controllers. Here's how it goes. First of all, you're transforming PS into P lambda. Okay. So you're converting it using Z transform. You're replacing S everywhere with 1 minus the thing. Okay. So you get some particular transform. Pay attention that this is order of the same order as S, which means your degree of the polynomials will not be higher or lower. You're not changing the degree of the polynomials in your transfer function, okay, after the transform. And you will get some sort of new value for P, but as a function of different variables. So it's change of variable, practically speaking. You're changing the variable, right? It's just particular mappings that you're doing to the variable. And you can write that again as rational function, as one polynomial divided by another polynomial. We will call the numerator polynomial n and denominator polynomial m. All right, whatever they are after the transform. So this is still, I'm working only on plant. Okay, I'm taking plant, replacing in plant transfer function s's with that formula. Okay, getting new type of thing with new variable, all right? Calling them n and m. Now I need to solve Bezout identity, okay? This is the tricky part, using Euclidean algorithm, which means this is Diophantine. You know what Diophantine equation is? Diophantine. So these are, let's see. So these are kind of arithmetical equations with multiple variables where the solution needs to be in integer values, okay? So you have equation with multiple variables, unknowns, but the solution needs to be in whole numbers somehow, okay? Which means that you might have actual unique solution to that, or you might have multiple solutions to that, but only in whole numbers. So here it's kind of similar type of equation which you need to solve, and you have two unknowns, x and y. So n and m are given polynomials, okay? And you need to find polynomials x and y such that their sum will be 1. Here you might have multiple solutions technically, but they will get to the same thing. So you are using Euclidean algorithm, and an interesting thing about that particular equation, okay, is that you can solve that using Euclidean algorithm. Euclidean algorithm of long division. Remember long division algorithm, arithmetic? Or like how you divide with that same one by another, and how you divide polynomials one by another. So this is our way to solve it. And like Euclid obviously solved that like 1,000 years before Bezout came up with that equation. Okay, so the solution existed like years ago. But that particular equation is easy to solve using Euclidean algorithm. We'll see how to do that actually. And then you're using inverse transform, you get n of s, m of s, x of s, y of s, and then you put everything into that formula for any given stable and proper transfer function q. Again, choose whatever q you want, but now you have a little bit more sophisticated formula, and you get all possible stabilizing controllers for UKs. So here is a simple example for that, right? The example goes like that. Let's say you have that type of plant, and obviously it is unstable because you have pole at +1. That's s minus 1 times s plus 1. All right, so one of them is at -1, one of them is +1, so it's unstable plant. So now we replace s with 1 minus lambda divided by lambda, okay? So here you get 1 minus lambda divided by lambda, here you get 1 minus lambda divided by lambda squared, all right? Doing some basic algebra, getting one polynomial divided by another polynomial, so you get n equals to something and m equals to that thing. Now all you need to do is to divide that polynomial by that polynomial, actually long division of two polynomials. So let's try to divide it and see what happens. So you'll get particular solution plus some remainder. All right, so this is how we typically get in long division. Let's see, it looks like that. Typically, you divide in lambda squared minus lambda by 2 lambda minus 1. Okay. So the first thing that you need to get is lambda divided by 2, right? So it will be lambda divided by 2. You multiply that one by that one, you get lambda squared. Subtract it later. Okay. Minus lambda half. Okay, so far. So this one minus this one is 0. Minus lambda minus lambda half, it's minus lambda half. Something like that. Okay. Now you need to get here, so it will be minus 1/4. right? So minus 1/4 times that thing will be minus lambda squared plus 1/4. That will be 0 and minus 1/4. Correct? Yes, should be right. Is it clear what I'm doing here? Or you never saw it before? This is long division of two polynomials. Okay, so now I can write z polynomial, which is, practically speaking, lambda squared minus lambda equals z polynomial times z polynomial, which is 2 lambda minus 1 times lambda half minus a quarter plus remainder. This is how you represent it. But now this part was n. So this is n. This is m. This is something. This is something. Now you can, what you want to do now is to get the equation which would be m. What's the equation? Mx plus my equals 1, right? So you want that thing to become somehow 1, right? So you need to multiply by minus 4 both sides, and you get something like that, minus 4 times lambda squared minus lambda equals minus 2 lambda minus 1. Now we multiply by minus 4 here, so we will get minus twice lambda minus 4 plus 1 equals 1. Something like that. And now you can do also plus, plus, minus. Okay. So what you get technically is exactly that equation. So have that part and that part are your x and y. Right? This is what that thing is saying here. This is how you got that. So x will be minus 4. Okay, this is what multiplies the n. This is minus 4. And this thing will be 2 lambda minus 1. This is what multiplies m. Okay, m equal to 1. And all of them are whole numbers. All right, so you get x and you get y, and you get inverse transform, which is that thing, 1 divided by s plus 1 instead of lambda. So you're substituting every lambda here is 1 divided by s plus 1. And then you get y of s, x of s is not changing because it's constant. And again, getting back to n of s, substituting 1 divided by s plus 1 instead of lambda, getting that thing, ms, substituting it here. Now pick your q, whatever it is, any stable transfer function, and you get the answer. Okay. So this is just one example for q equals to 1, which is pretty stable. You can get that particular controller. Okay, but you can choose any other q with given values, whatever you want. Just to mention one last thing, you can do the same thing for state space. Designing that controller using state space. Let's say you have matrices A, B, C, D for your plant. So you can find open loop transfer function, which is PS. Again, solve that same equation. Bezout equation, okay? And then you can design any controller K and any observer L which are stabilizing the system, whatever they are, and compute all of these values based on your design of your controller K and observer L, right? Then your closed loop controller, which will stabilize your system, will be written exactly the same formula as before. Okay, this is another connection to state space systems. All right, many questions? All right, thank you.